I'm going to design and to explain the circuit diagram. Circuit diagram of switching mode power supply. So switching mode power supply stand for switching mode power supply, and is used to convert AC into AC voltage from one level to another. So here I'm going to design the circuit diagram. First one, we have a cable here to plug into outlet socket. From the cable there is a protection, a fuse. This is a symbol of fuse. So we add a resistor. This resistor is called varistor, is used to protect against transient voltage. And above we have inductors with capacitors here. So this block here, the two inductors and capacitors, they are called EMI filter. They are used to protect against interference. So the next stage is bridge rectifier. Bridge rectifier is 4 diodes. So we have diode 1, diode 2, diode 3, diode 4, and here we have input. The two terminals here are the input, and we have output here with filter capacitor. So the next, we have two resistors here. R1 and R2. We have two resistors here which are going to supply this IC, is called power IC or pass wide modulation. So the two resistors here, they are called startup resistor. They are here just to drop down the voltage. The voltage here at this point, the voltage at this point is 300. We have 220 voltage. Even here we have 220 voltage, but the output voltage increase. So we have the output here, which is going to supply here to this transformer, and the output of this IC is connected to MOSFET. This is a symbol of MOSFET, and the MOSFET is connected here to the primary winding of a transformer. The function of this power IC is to provide a variable signal. The function of this MOSFET is just to switch on or off. So this is connected to ground. We have another transformer. To this transformer we draw here a diode with a small resistor, and they're coming here, they are connected together with the voltage source applied to this IC. The diode and resistor, they are called startup resistor. So here there is what is called freewheeling diode. We have a diode here with capacitor, and across this capacitor we have a resistor. So the diode here is used to flow the current when the switch, the FET, is in off state. Means the current discharging through this transformer is passing through this diode, and the capacitor here is charging, and the resistor is discharging directly. So here this is a primary winding, there is secondary winding, one terminal is connected to ground, and we have a diode. The diodes here, they are called half-wave rectifier. The half-wave rectifier, why is called, they are called half-wave rectifier because they are only one diode. So at the end we have filter capacitor. The filter capacitor here is having two capacitors and inductor. Is called pi filter because depending on how is constructed. The same here we have filter capacitor. So this is DC output. Here we have the same, we have inductor and we have capacitor. So this is the output DC. Means the filter here is just to clean the output per setting. DC means to have a pure output voltage. So let me take one of output, let me call B plus, the output to feed back to the input. Here I have a resistor, two resistor, So the resistance here is what is called voltage divider connected to ground and is passing through this regulator, and the regulator is providing the current to photodiode, and here we have a transistor. Means this stage here is called optocoupler. Means the output here on corrector, this is emitter, but the base here of this transistor is not having a base, means that this is called a phototransistor, and this is feeded back to the power IC. What will happen to this circuit? So when the output voltage increase, will feed it back here, and the voltage here will change. When the output voltage increase, will increase also the intensity of current increase, the light of this photodiode, and the voltage at this point of corrector increase. So means the output, this IC is here to do what? To compare two signals. There is one signal generated by power IC, and there is a DC voltage which is feeded back. So the power IC generate a signal which is rectangular wave like this. I told you that we are going to compare two signals, the feedback signal and the feedback signal is DC. For example, is 5 voltage. Is DC like this one. What will happen when the signal from 0 up to 5 voltage here the pulse is passing to the gate of transistor, means is passing when the voltage is above 5 voltage, means the output voltage will be this one. Okay, what will happen when this voltage decrease? For example, decrease to 3 voltage here. You see when the voltage decrease, you see the pulse is very wide. When the voltage decrease, the signal is very wide. When the voltage increase, the voltage is narrow. So what does it mean? The output voltage is equal to the voltage input times duty cycle. D is duty cycle. And the duty cycle is equal to time on over period. The period is starting from, means here the period is this one. So when the signal is very wide, means the T on increase and the output voltage also increase because the duty cycle increase. This is the duty cycle. So what does it mean? The output voltage, which is the voltage in times duty cycle, the duty cycle increase, the duty cycle increase when the feedback decrease. So in switching mode power supply, there is what is called auto-regulation. Means when the output voltage decrease, the IC will force the output voltage again to increase. So when I come back here on this block diagram, this is a fuse, and the fuse here is to do what? Is just here to protect over current. We have another block here. This one is called varistor. To do what? Means to protect against transient voltage. And we have another block here, means which contains capacitors and inductors. They are here to protect against interference. And we have bridge rectifier to convert AC into DC. We have two resistors, startup resistor to do what? Means to drop down the voltage. We have this IC to provide a signal to the gate of this MOSFET. Of course, this MOSFET is there to switch on or off the primary winding of a transformer. Here we have secondary winding of transformer. Of course, we have three here, which are providing three outputs. We have diodes here to rectify or to convert AC into DC, because voltage here is AC, AC, AC. And we have also this stage is called capacitors. They are here to provide a clean DC, and there is output which is feeded back. Here we have two resistors, which is voltage divider, means the output voltage, we have the voltage here which is decreased. We have a regulator, we have optocoupler, which is here to link the output and the input, and we have the output. So when the output voltage increase, means will increase also the voltage coming here on this power IC, and this will force the voltage which is supplying this MOSFET to change, and this one will change also the output voltage. Means as the output voltage decrease, this IC will force the output to increase. When the output voltage decrease, this IC will force the output to increase again. So there is no a special regulation here. Simply how the circuit is designed is here to regulate, to make output which is constant itself. There is no external component which is here to regulate. So this is the end of my tutorial. Don't forget to subscribe to my channel, and for any comment, try to write down where there is written comment, and is better also to share to other. Thank you. This tutorial, I'm going to talk about universal logic gate. Universal logic gate. So we have two types of universal logic gate. There is NAND gate and NOR gate. So why they are called universal logic gate? Means it is possible to implement any other logic gate using either NAND gate or NOR gate. So how we can implement other logic gate using NAND gate? Example, implement logic gate NOT and or NOR using only NAND gate. So first I'm going to implement NOT gate using AND gate. So here we have input is just to connect two input here together. So when you take NAND gate and you connect the two input, the gate became NAND gate. Means we have A here and we have A here. A dot A naught. This is equal to A naught. Means this is not get using only NAND get. How to implement AND get using NAND get. We know the expression of AND get is A, B. So to solve this problem, we put here two bar here, which means we know that when we have A with double bar means is equal to A. Always when you make a double complement to any expression or literal means there is no anything you change. So let me try to draw A dot B so here we have A, B, the output is AB not, and the output here is AB not, and this is equivalent to A to AB. So means to implement NAND get, we implement AND get when you have only NAND get. This is the only circuit you can use to implement AND get. So the next one is OR get. So I'm going to implement OR get using only NAND get. How? The expression of OR get is A plus B. So simply the way to solve this problem is to complement twice here. Is just to make a double complement. And remember that this sign is not corresponding to NAND gate. I'm going to remove. Based on De Morgan theorem, A plus B is equal to A dot B, like this. So this is the way to remove this sign. So this is equal to A B naught. So I can draw this is A, this is A naught. We have B, this is B naught, and here we have, so the output here is A naught B, like this one. So and this one is equal to A plus B. So this is the way to solve the question like this one. Next, we are going to implement NOT get. NOR get using NAND get. So we know that NAND gate is the expression. The NAND gate is NOR gate is this one, A, B, and the output is A plus B not. So we are going to implement this using only NAND gate. So X is equal to A plus B. This is the expression of, so I'm going to complement twice here. And how to remove this sign, because this sign is not matching with NOR gate and NAND gate, is just, this is A dot B using, so we have A, of course A not is, we use NOT gate, B, so we make a sum here, and the output will be connected again to NOT gate. So here we have A naught, we have B naught, A naught, B naught, whole naught, and we have A naught, B naught, okay. This is equal to A plus B complement. So this is the way to implement. Let me change again this question. Implement NOT gate and or NAND using only NOR gate. We use the same procedures. For NOT gate, just is to draw NAND gate and you connect the input together. So when this is A, this is A, this is A, is A plus A naught, and this is A naught. So second, for AND gate, using NOR gate. How to solve? We know the expression of NAND gate is A, AND gate is A, B. Just what I have to do is to add 2 bar here. And you know, the sign times is not matching with NOR gate, so the NOR gate always requires plus sign. So what I have to do is to use De Morgan theorem to change the sign. This is A, B, and I add. So this is A naught, B naught, and the output here is A naught plus B naught, and this is equal to A dot AB. So By using the circuit means we can implement AND gate, OR gate. For OR gate using NOR gate, simply we know that the expression of OR gate is A plus B. So to implement using NOR gate means I make a double complement here. So simply the remaining is to draw. Here we have A, we have B. This is enough, means A plus B naught, and this is A plus B naught, and this is equivalent to A plus B. At the last, let me implement NAND gate using only NOR gate. So we know that the expression of NAND gate is this one. What we have to do is just to put double complement, and using the Morgan theorem we can change the sign here. So I can draw A and B and B. So the outputs so means here we have A naught, B naught, A naught plus B naught, A plus B naught, and this is equal to A B naught. So this can prove that using NAND or NOR, it is possible to implement or other logic gates. Means you are in the workshop, you have only NAND gate and NOR gate, and you need to implement all remaining logic gates. So it is possible, is the reason why they are called universal logic gates. So this is the end of my tutorial. Don't forget to subscribe, and for any comment, try to write down where is written comment and to share with others. Thank you.